Good morning, my outstanding, wonderful, intelligent, super electronic friends. Well, what are we talking about today? Albert Einstein was right again. Astronomers have detected light from behind a supermassive black hole. Well, this is not to put Albert down, but he wasn't right about much. All right, and that's what I'm going to tell you right now. You can, oh, Roger, oh, show me what he wasn't right about. Well, I will. Absolutely, I will. Now, what was he right about? He said that light was a particle, not simply a wave of just nothingness. And he was right about that. But the particle itself is nothing more than a magnet. It has a positive and a negative pole. And as it goes through the air, everything else has positive and negative poles. So it has to push its magnetic field through the air. That's why it's a particle and then a wave in front of it. I'll show you this absolutely no question about it. Now, this is what happens in a black hole. The center of the black hole actually literally takes in dark matter in the center and wraps all of its explosive material around it. And I will show you this in our light experiments. It's very, very obvious. All right, are you ready? Here it comes. Okay, let's talk about what Albert had to say about light. Now, we all know he said that light has a set definite speed, and he calculated it as c. And E equals m, which is mass, c squared, which is the light squared. Why he did that, I have no clue. It makes no sense, but let's just go on from here. Now, light is a particle, and you see it as a wave. We can see it as just a wave. That's all it is a wave. No, it isn't. It's a particle. And how can I say that? Well, because I will show you the particle, first of all. Secondly, the particle is way back here. And it has a magnetic field around it, just like all magnets. And they have a field around it. So as it goes forward, the field precedes it, just like this. Therefore, you have a wave in front of the particle moving all of these other gaseous particles which have electrons attached to them. They have to bump against these electrons which are flowing through the air, the magnetic field, so they begin to glow as this glows because they are impacting. It's called push to shove. Anytime an electron, which is everything has electrons, concusses with anything else that has an electron, and everything has electrons, it creates some form of heat. And that is what you have here. That is concussion. And it creates heat. You scrub your hands together, and it is electron against electron. You have heat. When you have conduction of electricity, an electron actually flows through a wire. Everything has to get out of the way. It creates heat. That's why when you have wires running a lot of electricity through them, you feel the heat. Simple as that. Radiation is these particles coming through the air, just like this one, impacting with whatever is in front of it. If it's gases, they glow, and you see a glow, and you see this radiation reflecting back because it's bouncing these electrons into those electrons, and they bounce back. Literally, it's a bounce. All right, so we have particle, we have wave, we have interaction, we have glow, we have the wave proceeds through the air, and the particle follows it. Now, can we accelerate this? If we can accelerate it, obviously Einstein was wrong. If that's light, and I know it's light, there's no question. If it can accelerate, then Einstein is wrong. And guess what? Now, if you could tell me that's not acceleration, I want to know your reason. And if you could tell me that that's not the particle that we saw, which is way back here, and I will show you that particle. Actually, it's a box of 4 little bits. 2 of them are positive and 2 of them are negative. And it pulls itself out of that wave like a rocket ship, and then it explodes here, increasing its energetic potential 200 times approximately. That's what they say. I'm going by their words, not mine. This is the light prior to its extreme acceleration, and interaction. So its energy value here is, let's say, 1. Its energy value here is 200. All right, it's just like your hand bumping here and saying, well, that's nothing. But if you slam that thing as just hard as you can, you're going to have some kind of really super energetic value. That's what we have here. It's identical. Identical. Okay, so now you say, Roger, you can't see light, you can't see photons, you can't see these subatomic particles. It's impossible, they're too small. I say, no, that's totally incorrect. You don't see the particle here, all you see is a wave, and you see a glow. Absolutely, I agree with that. You're not going to see the particle here. No question whatsoever, you are correct. However, if we can accelerate that, and pull that particle out from its wave and make it concuss, we can see it. And here it is right here. There's the particle. All right, it's back-to-back dipoles. A dipole means a positive and a negative. That is what we would consider a positive, and that is the negative, which is the electron. We've always been able to see the electrons. We can see the glow, we can see conduction, we can see all of the evidence of the electron. We never, ever, ever saw the evidence of the black particle, which is dark matter and the muon. All right, the muon attaches to the electron. When they hit another medium, they shower into what's called Cherenkov radiation, and at that point we see them literally separate. Nobody's ever known this before. It's been done. They just had no clue. And here is exactly where it separates. We just saw the black and white ball. All right, they were attached here. What happens is when that particle, that same particle I just showed you, accelerate, it starts to back up and crush against its own fields. That's when you see this glow start coming. And then the glow becomes absolutely intense and they separate from each other at this Venturi, which is a slit that has 2 round cylinders here. And the light has to force its way in between there. When it does, it expels the black particles and the white turn into showers. Exactly what CERN says, but they have never seen this because they have never been on this level. They are on a level which does hundreds of billions of particles at a time. We use 4 particles. So you saw the light accelerate, and then it started to glow here just before it hit the Venturi. And at the Venturi, which is right here, and don't forget it's 2 little curves, just like this. And the light has to force itself, which is, as I showed you, it's a ball of magnetism, a field. And the particle itself is in the center of that field. That field has to crush. When it does, it simply crushes the black particles away. I never thought this was possible. I would have never accepted this if I hadn't seen it. Because we are seeing actually the dark matter, the black particle, which is dark energy, dark matter, whatever you want to call it. It does both things. Dark energy means it's gravity. It's gravity. It's not expelling energy. It's gravity. It's dark. Choom, pull me in and hold me tight. That's what this does. This is the only time anybody's ever seen this, is when there is a catastrophic collision of particles. And they do this with that accelerator. They send them around and they smash head on, and they see these particles, yes, but they have billions of other particles and chunks and blobs and hand grenades of all kinds of things going on in there. And then they see these tiny little particles and say, wow, look at that. Whoever expected that? Well, nobody did. And they still can't understand it because they have started out with a mass that's so enormous that you could dig for a million years and never understand what these particles are. You have to start like we did with light. Light is light. It's as small as it gets. It's all over the place. It's everywhere. And you just don't even realize it's there. It's just flowing through the air. Well, we can actually now visualize not only the flow of light, which is that field that I showed you. we can visualize the particle that is inside the field, and then we can visualize the impact effects and what we would now consider mass. This particle back here had virtually no mass at all, almost nothing. When it concusses, whole different story. Mass is energy. That's all it is. And mass, though, is not just like a chunk of something that weighs a pound. No, it weighs a pound when it's sitting there. But if you threw that thing at 10,000 miles an hour against a wall, it's no longer a pound. It's 100,000 tons. Well, that's a big, big difference. All right, so you have rest mass and you have energetic mass. Two completely separate entities. A tiny particle here can be extremely energetic and have energetic impact value that exceeds its original value hundreds of times, which is the case right here. The particle back here was a 1, and the particle right here is 200. That's an increase in its energetic value of 199. That means if we can use some of that to re-establish this feed, then take the excess, we have free energy. Now, so you understand, coming in to the Venturi, we had a muon neutrino attached to an electron neutrino. That's the black ball attached to the white ball. Now, at this point right here, you see the concussion begins, and we begin to create electron showers, which is the white shower I just showed you. And the black ball does nothing. It just stays exactly the same, the muon. I agree with exactly what they're saying here. However, they have no clue that these are electrons. That is literally an electron together. Attached here, it's an electron. Here, it's divided, but it'll come back immediately, instantaneously, back to its original electron muon form. All right, here's a pretty good close-up of it and showing the energetic values. We see this just before it explodes into bits and pieces, and I'll show you that actually occurring. What is the energetic value? The forward-leading white particle is the concussive particle. This will spin, it'll wobble, it'll do all kinds of things. Either one of these can become extremely excited, but it has to be the leading one. Now, the dark energy just it doesn't do anything. It just has no impact value whatsoever. When you force these particles through the Venturi, it just pushes these away, and the white ones just continue on through. The black ones, for some reason, I'm really not 100% sure of the reasoning behind it, but I can see what I'm seeing. Now I have to try to figure out why it's doing it. I would have never, ever, ever in a million years accepted anybody telling me that you could charge separate, which means you could separate the positive from the negative. I would never have accepted that, but we can push that right away from that particle. I don't know how, but it just happens. All right, so you can see that we can see the black balls have separated from the white particles, and then right here they come right back and reattach, and this is like instantaneous for light. Now, just instantaneous, basically, they reattach. However, there's just enough distance to put in a solar collector right here, a harvest plate, so that we can take these raw white electrons, no dark matter attached to them, so they are like 200 times more powerful than they were when they were attached. That is what they say. If we can harvest it right here, we have 200 times more energy than we started with. So that obviously leaves you excess energy. That would be free energy. And this is an extremely simple device. And it does exactly what they claim. It creates these electron showers and these muons. And they say the muon and the electron shower, when you concuss it, you can have 200 times energy that you started with. That's free energy. That's what we're looking for. That's what I'm looking for. All right, I have some very talented people doing this research on the experiments on light. Now, this is the Higgs fields in extreme acceleration And this is what they look like, enhanced. Now, I don't do the enhancing, I don't do the experiments, I do the atomic theory. And it's called electron flood theory. And these are the particles that we're dealing with. We saw the light, we saw the acceleration, we saw the particle, we saw the Higgs fields. And these are the leading tip of the spear here, so to speak, the tips. There you still see the black energy in the center and the white energy surrounding it. Now, why do we have some down in the corners here that are also, these are, all it is impact. Impact causes this particular look, that surrounded black field with white electrons. You see them right there? 2, 4, 6. It makes this exact geometric pattern. And that is exactly what you see here, an exact geometric pattern of the Higgs fields. There's a lot of work to do here, but this is, anytime these things have an extreme amount of concussion, you see the black and the white separate. And this is, it's being pinched here. You see this pinch? That's why these are glowing more. They're behind the leading edge, but they're being crushed sideways. Just exactly like this was crushed sideways. These are all red particles. This was a red particle when it started. But you see this one here? And you see this one here? They impinged upon this one's disc, crushed it, forced it to squirt out like a tube of toothpaste, and increase its color to blue, which is extremely more energetic than the red. So not only have we accelerated them coming through the Venturi and turned them into red Higgs fields, we have additionally re-accelerated a Higgs field and turned it blue. That's pretty amazing stuff. And again, I don't do this, so I'm not taking credit for this. I'm taking credit for the atomic flood theory, which was my flood. The atomic nucleus is a dipole. All right, it's a dipole. It's made up of all of these little electrons, and 1,839 electrons make up one proton. 1,840 make up one neutron. So a hydrogen is not one big gigantic positive and one tiny little negative. No, it's 1,840 or so central electrons creating the core, and then it influences one more or so around it that want to get in, but they say, no, you have to stay away because we have plenty in the inside now. We're fully all set here. You're going to have to stay out here. You can't get down in here. We're congealed. And I'm just showing you this to sort of give you a ball effect. But the actual core is nothing. Well, let me just show you some little doodles about what it's like. All right, you saw, this is the new model, is the electron flood theory model. Bohr, forget about it, never worked. Gigantic positive center and a bunch of little negatives floating around, just impossible. And I knew this 50 years ago, and I fought like hell, and I never won until now. Nobody can dispute this. If you can dispute it, I want to hear you dispute it. Tell me why I'm wrong. And you say, oh, you can't see electrons. You can't see electrons because of this is done with a cell phone. These are Samsung cell phones. They seem to do a hell of a good job. Wait till you see some of the nighttime pictures. Woo-hoo-hoo-hoo. The only reason you see these dark balls with the white around them is because they're coming at us so fast that the dark matter is trying to gobble up white matter. Now, you would never see this unless it was coming at us as like a rocket ship. You would see this. You'd see these. And you'd say, well, those are electrons. Yes, they are. Well, what is that dark core doing in the center there? Well, that dark core is dark matter. Now, we saw the electrons, and you would never see that black ball unless they were highly accelerated. Again, you would see this. You'd see that. You'd see these little white glowing things, and you'd say, well, that's an electron. Well, good. But it has a dark side you never saw. It's inside the white. Now, when you concuss them, you separate them. They divide. And I'm going to show you it actually happening as the light flows through the air. Just as it concusses, it explodes. Now, again, a photon is 2 electrons back to back. And that's what's coming through the air at us. Now, they can divide, as we saw. The black can go away from the white. Very, very unusual. Now, a proton is the first number of electrons that become stable. And all it does is get bigger and bigger and bigger and bigger and bigger and bigger and bigger. And that's what these are. It's the tiniest one, hydrogen, helium, and they go up lithium, all the way up, like a snowball. And that's all it is like a snowball, like that, with a dark core. Because the dark particles have no problem touching each other. They'll lay right on top of each other, no problem whatsoever. The white ones just get away from me. That's why you see all this separation. There's a certain distance. They say, stay away that far, and you stay away from me this far, and we're going to be okay. And that's exactly what you see there, is a separation by quantum distance. Just look it up. Quantum is all it means is a distance, a separation. Tiny, tiny little angstrom unit distance. You have to stay right out there, and then we're going to be okay. I will push you, you will try to shove me, but we will stay right there, and then we're going to be okay. And that means my core has plenty of electrons. I know you want to get to that dark matter because it's more attractive than the white matter. So you're going to try to get in there, but I'm not going to let you in because I have enough electrons. I have all the electrons I want, the white particles. Do not try to get in here. And it'll say, I'm coming, and they'll say, no, you're not. And they'll stay just exactly a distance away from the core. It will not let it in. That's what's called orbitals. Those are your quantum distances. And those quantum distances relate literally into colors. The further away you get, the less bright color you get. You get red way out at the end. You get blue very close to the center because that's the high-powered particle. And then as you get lower and lower and lower in energy, you end up with a red. Red is the lowest of all energies. The blue is the highest. And then green is right in the middle, and then yellow and orange and all that stuff. Now, let's just keep going. Now, the light experiments we were doing literally was with a construction laser, just like this, pulsed red laser, pip, 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 and it receives them back. We don't care about the receiving. We care about the pulsation of those light waves. Now, all we did was put it through two round cylinders in between, which made the fields crush each other. That expelled the dark matter, and we could see it. And the reason we could see it is because what's called radiant intensity. And the radiant intensity means the reason we could see electrons is because they glow so brilliantly under this specific interaction of crushing it into the Venturi. Now, if we hadn't done that, you would never have ever seen those particles divide. Now, there are new, and that was with a cell phone. That was straightly with a cell phone, right on top of the Venturi. Just simple as that. This went through two nails like this, right attached basically to the front. In between the two nails, out the other side came the electron shower. It's just happened. So the two nails created the curves to bring the light crashing through there, and on the other side, again, strictly with a cell phone right on top, watching for it. And Rod, who is doing this research, says that he's doing some other stuff now, working with prism type glass and stuff. He says you can actually hear the light crackle when it's going through some of these orifices. It actually crackles, he says. That was his words, not mine. Now, what is this? This is Rod's nephew, Dylan Carpenter. And he sent me this, and I said, whoa. It's freaked me out. I said, where did you get this? And apparently, all he did was take a Samsung, he called it, I think it's a Samsung 820. It's a brand new Samsung phone. And all he did was take a picture of the moon, apparently, at night. And this must be a star. Now, I don't have the details on this, but you could do it yourself. If you have one of these cell phones, he's doing something. I don't know what he's doing with the manipulating the fields and so forth. But the same thing happened with the other guy, Fabien Brulé, who did the enhanced, those pictures I showed you, all the black and whites and all that stuff, the fields. He did that. Rod did the experiment, the original experiment that showed we could separate light. Now, this was from Dylan. look at this now. You take your time. See, here's the problem. People say, "Ooh, look at that, it's fancy," and they go away. Think about this very, very carefully. We've got dipoles here, and the dipole just means a white and a black. Let's just think about it that way. It's a positive and a negative. All right. These are all dipoles too. Every one of them. You see? They all have a dark side and a white side. Now, they're bigger and smaller stars, it appears. And this baby here has got some serious energy. Now, this, I believe, is the moon. Now, what's going on with the moon? What's this little blue stuff going on here? And what's this little increased yellow going on here? Now, let's just stop and think. Stars radiate. All right? They don't absorb and re-emit. They radiate their own energetic value, just as the sun does. So what are we seeing here? The moon does not do that. The moon reflects. So we're never going to get a whiteness from the moon. We're going to get reflectivity, which is in this case the yellow range. Now the blue up here has to be more impactful. We're getting something there is giving us more brightness than the rest of the moon's surface. Whether it's because it's crushing through the air, we're all spinning through the space. And the moon does not spin in circles, it just flows around with us. So I'm not sure exactly whether this is the impact of the sun on the back of the moon or whatnot. I have no clue. But I can see these energetic values. It almost looks to me like these particles here are on this side of the moon facing us. And I would have thought they were stars, but I don't think there's any stars between us and the moon. None that I've ever heard about. But these particles clearly appear to be within his view, which means that they have to be this side of the moon. Unless somehow they're curving around the moon, which is a possibility, because the moon has a gravitational influence, but I don't know if it's that much. And then you can see all the magnetic fields. These are magnetic fields, and they're just obviously magnetic fields. The way they wrap around and the way you see how they're tight, loose, and then all of a sudden they get to a point where they just really don't have any attraction anymore. Now, you see this dark and then a white side, and you see the white side and then the dark side, dark and then a white. It appears that these fields are a field of darkness and a field of whiteness, a field of whiteness and a field of darkness. And they just opposite of whatever, like in other words, this is a white field, and this one here is going to produce more of a dark field. You really can't see it, it's cut off here, but I believe that's what you would see. You would see a darker field here, and this is a whiter field. Same thing as you see a darker field here and a whiter field underside. So it's opposite of whatever the color of the charge is, this is all very, very difficult to understand, and it's brand new. Nobody's ever seen this before, so it's not like anybody's got any real good answers yet. But this should spark some interest, I would hope,